So it's a great pleasure to have Pavlo Dral here with us, guys. Pavlo, okay, is a professor in Xiamen University, and uh, one of the main expert on machine learning today in the era, applying this technique in many applications like molecular dynamics as well, but also quantum dynamics, and also having many very good materials, okay, shared in YouTube channel, also in social media. Uh, Pavlo, I combine it with Professor Pavlo, okay, a lecture, and after the lecture, okay, officially we can have the Q&A session where people can ask him, okay, about the lecture. So we can record the lecture and then share this for the community after the this time here, okay? So Pablo, please, thank you a lot. You can talk.
Okay, thank you very much. So if you have any troubles hearing me, seeing the screen, please let me know immediately so that we can restart without interrupting, without repeating much later. And if you have also questions, drop them in the chat so that I can see them, and then I will try to reply as soon as possible. So we'll try to make it more interactive, and even my first slide already like calls for interaction here. So I love to show this. I was sharing it also on Facebook and LinkedIn and other platforms because it's one of my favorite examples that I show to my undergraduate students here when I teach computational chemistry and AI. So like so you already know what is molecular dynamics in previous courses, I believe, so I don't need to explain what it is. And here is application of machine learning to MD. And so this is a simple hydrogen molecule, H2, right? So two atoms of hydrogen, and they don't do much usually, right? So quite boring molecular dynamics. But if you now look closely, so you probably see something very weird happening here. And like anyone can, especially from students, tell what is wrong with this or what is weird here going on with these dynamics. So this is pretty obvious. And then we'll start from here and try to explain what machine learning can do, what it cannot do, and what you should take care of. So anyone wants to say what is weird with these dynamics. So it's pretty obvious, but so this is very simple example, and I will show you later how you can run this yourself. Also online. So guys, don't be shy. You can just chat or unmute yourself. Just go ahead. So if it would be offline lecture, I would just pick anyone and pass. So maybe I can ask here offline, what about, I hope I pronounce name correctly, Jared or Jared?
Jared.
Okay.
Yeah, the atoms is very have a great superposition when they are very close.
Yeah, I mean, obviously in molecular dynamics, like you should not see this. So you see like 1 and 2, so atoms. So they start, one was here, then it tunnels through 2 and becomes on the other side, right? So that is definitely like what cannot happen in any reasonable like physical simulation, because how nuclei can go through each other, right? So that's impossible. There is too much repulsion there. But you see, like machine learning can give you such dynamics. And that's why it's my favorite example, because already here from the very first simple picture, you start to understand that when you apply machine learning, many things can happen. And it also allows you, so machine learning is super flexible. It allows us to do things which we couldn't do before. It's very fast, so it runs in dynamics, you don't need much time. But because it's so flexible, it's sometimes too flexible, right? Sometimes it completely ignores physics laws if it didn't have it in the data, or you didn't hard code it in some clever way once you were building your machine learning model. So that's what I will talk about in this lecture. How can we properly apply machine learning to MD? What is current state of the art, and such questions. So if you have, again, like any questions from previous lectures, and once you're going, just unmute yourself, ask, or like drop some message in the chat. I am keeping the chat open here. So of course, molecules are always in motion. That's why we want to simulate this motion. And how we do this is very well known for you already. So typically we solve very simple Newton's equation of motion, which we learn in school. What is not so simple, there are many algorithms how to do it, and there are also like many considerations for preserving physical quantities, like energy conservation and other things. But in principle, the equation is super simple, and then everyone can code it like by following some textbook or try to derive yourself. So it's not very difficult. But the problem is, like, all of these things, like, you need to do many times with small time steps, right? So what we usually have, we start with initial conditions, positions, velocities, then we get some gas based on these equations that I showed you before. And you get new position, and then for these new positions, you will calculate forces, and you basically repeat all of this, right? So this is a quite simple process, but again, it takes lots of time. So if you try to calculate MD trajectory of H2 molecule with DFT methods, like this REAP is popular DFT method, and you can do it if you use our software emulator, like simple input file. So you specify KMD, psrelip, 631G star. You can also do it in Python. So time step, usually we have very small time step, because if you choose too big time step, molecule dissociate. We'll discuss it later. And then you say how long you want to propagate. And even for this experiment, see, it's like 500 with 0.5 time step is already 1,000 points. So you need to calculate 1,000 times, to be precise, like 1,000 times DFT calculations for this simple molecule, right? And then repeat it again and again. So this you can do. That's pretty fast, but it will still take some time to do. And then for bigger molecules, obviously, it will take much longer. So I just showed you input file. So we have this software which we developed already from 2013. So our initial goal to provide black box software to do both machine learning, quantum chemistry. But initially, the goal was to really bring machine learning to be as useful as and easy to do, like you would use Gaussian to do quantum chemical simulations like DFT calculations, right? So just simple input files, now Python. The idea is to make it as simple as possible, and nowadays it's really growing rapidly with bigger and bigger user base. I also have a course which you can register, so I will open for you. But when you register, please use your academic email address so that we can open it faster. And then you can check this course. So there is a section about molecular dynamics and other things which I will talk about. Although the up-to-date version needs to be done. So these things really change fast. That's why our goal is to make it live course. So that's why, again, like you can register here. So there is also a book which is more formally discusses all these topics, but it's 27 chapters and you cannot update it. It's printed. Okay, so my question is now, second question is like, how can we use machine learning to accelerate molecular dynamics? And I believe you should have already know and heard many approaches from other speakers, from lecturers, from social media, from papers. So any ways how you can use machine learning to accelerate MD. And I might pick up someone randomly again, but you can just unmute yourself and go ahead. And this is, don't also rush, because although it's a simple question, there is a small trick there, so I will talk about it. So how can we use machine learning to accelerate MD? Anyone?
Yeah, Pablo, maybe using the data, maybe implementing machine learning for improving the force field parameters, or getting the parameters for the force field, and classical MD, yes.
Yeah, so that's actually a very good point. So I'm not going to talk much about that, but in principle, yes. So like people use machine learning to use. So there are many ways. So that's why I'm asking you. So that the most obvious answer. So you didn't say it, right? But this one is a very valid way, and many people try to use now machine learning to have better force field parameters. What I did myself at some point is to improve parameters of some empirical methods, not specifically for molecular dynamics, but to do some simulations. And so in principle, you can do this application of machine learning. So that's a probably even very good approach, although it's harder to do, and that's why fewer people do. So does anyone know like more popular approach or any other approaches how people apply machine learning to accelerate MD? And actually, so like if you improve force field parameters, you improve MD, right? So accelerating, I don't know, it might be slow actually. But accelerating MD, how do you want to accelerate it? Okay, so one option is to use ML to describe, so Alexandra Moni Pereira says, one option is to use machine learning to describe the energy surface and run the simulation without the need to solve the force field equations. Fine, so describing energy surface, yes, but it's the same as force field then, right? It's just machine learning force field. So you will still need to solve the force field equations. Or maybe you mean something else. But that's already closer to what is the most popular approach right now. So anyone else wants to clarify, like to answer this question? Because that's very interesting. So like if you think about these questions, although they are standards and many people have the same answer usually, like who work in this field, it's always interesting to ask it, especially undergraduate students. They have lots of interesting ideas, and you can come up with some nice project for that. So don't be shy, like think a bit out of the box maybe.
Yeah, I think I can add something.
Yeah.
I think that we can use it to solve problems when using, for example, AI molecular dynamics, AI, no, ab initio molecular dynamics, will take a too long time. For example, diffusion of particles within a liquid or solid.
Okay. Yeah.
To study this kind of thing will take ages to finish in ab initio molecular dynamics, for example.
That's right. Yeah. So, but how do you want to do this precisely?
So if someone else wants to add something, please feel free. But training, getting different configurations of the system so that the surface energy potential could be described in a fair way, and with these configurations, train a model to obtain the potential.
Yeah, that's a good one. So, like, anyone wants to say how to do that? Okay, so somebody says here, I really love these discussions because you get many ideas and that everything is valid. So, like, that shows the versatility of machine learning, right? So, like, people say predict. So Gabriela says to predict results of simulations, so that you don't have to run so many calculations. That's actually a very, very good point because sometimes you don't even need to do MD, right? because sometimes you run MD, or not sometimes, but very often you run MD to get some statistical property, right? And that can be done actually directly without running MD. So like you can predict directly Gibbs free energy or something like that, like just give it some energy. So another, Luciano says, working with machine learning teratomic potentials connected to Marcellody. So that's exactly what I was kind of pointing to. So that's true. And then, so that I will talk about is machine learning teratomic potential. So that's exactly what I was kind of hinting at. And then there is dataset. So Natia says dataset preparation and finds the optimal machine learning model using training various ML models. Right, but then you need to say like, what do you want to do? So like, what do you mean by optimal machine learning, and what is this machine learning model, right? So, and what is the data? So that's why when you think about machine learning, very useful trick is to, especially if it is kind of supervised or even diffusion machine learning model. So like, if you think about this in the way, what is your input and what is your output, right? So like, the question can be reformulated. What do you want to train your machine learning on? What is data contains in your like data set, right? So like what is you put in machine learning and what you want to get from the other side of machine learning. And that is super like underappreciated, but a very useful thing about machine learning, because machine learning is really flexible to do many things that allows you to discover and design many new novel approaches. So I will talk about that later, but let's go to the classical one, because that's something that the most mature, the most developed, and then you will see it everywhere. So we cannot go away from this topic. So machine learning into atomic potentials, or just simply sometimes machine learning potentials, or machine learning force fields, you will find different names for them. So that's what exactly they do. What they do is they basically accelerate prediction of energy. Nice. So like to get energy from quantum mechanics, like DFT methods, it's very, very slow, right?
Professor Pavlo, sorry, I think your slide is out. Yeah.
Oh, okay. Let me try to share again. So good that you. Okay.
I'm sorry to interrupt you, but
Yeah, it's good, good. So like that's what I asked you. So can you see it now or still not?
no, I can't.
Yeah, it's not
Now
working.
Oh, it's
it's coming.
No, now it's good. Now it's good. It's good.
Excellent. So
Thanks.
In,
I was,
in a better way.
yeah. So I hope that you can see now that this E potential, right? So E machine learning potential, right? So this is the energy is a typical property we want to predict with machine learning. So that's the most, again, mature, the most common application of machine learning right now is the literature. There are many methods which take coordinates of your molecule or the big system, right? And then they predict as output, so as input they take coordinate and predict as output energy. And that is super slow with ab initio approaches or DFT approaches, but it's very fast with machine learning. That's why it's so popular. And you can train it on this ab initio data, so you can predict these energies very accurately. And once you take derivative of this, you get negative force. So then you can use this gradient. Oops, I think it again disappeared.
Yeah. Disappear it again.
Okay, that's weird. Okay, anyways, I am sharing again. So keep describing this. I think it starts sharing right now. So that's the way how we typically accelerate molecular dynamics with machine learning. So very simple. We just predict potential energy faster. And then we do the same thing as we would do with DFT or any other approach, or force field. So the difference to force field is that it is actually slower than force field. So force field is still faster. That's why people now develop like combined schemes of molecular mechanics and machine learning. Like previously it was QM, MM, right? So now they try to replace QM with machine learning, and then put still like biggest part of simulation is done at the molecular mechanics level. But the advantage with respect to, so compared to force field, molecular mechanics force field, is that it is much more accurate if you train it directly on ab initio data, right? So it's not perfect, but it's now very popular because it solves many problems with speed. So that's why we try to use it. And if you try to do this with machine learning, so that's what I did with ANI1CCX approach, which I will talk about later. So if you take the same input file as I showed you before, but replace BCD with ANI1CCX or other machine learning model, even your own model. So we have this course. I will not talk about like technical details, how to prepare Python scripts and input files. You can find it in my course, but I am just talking in general that if you replace it with this machine learning model, which was pre-trained for you, then you can propagate these dynamics much faster than with DFT. And then, I mean, this hydrogen molecule, so you will not get much speed up. But for bigger molecules, you will get much more speed up. And this actually dynamics is coming from this ANI1CCX machine learning interatomic potential. So this potential, I'm not just bashing it because it's actually very good potential for many things. But it may produce these kind of situations, so then you have to be aware of this because now there are lots of potentials, and once you use one of them, you might come into such a situation, and then you should not be surprised. But let's think about how to explain this in physical and now. Like, it was done with machine learning. So any guess what went wrong here? Because you might already heard, like, machine learning is now very popular. You might have some courses about machine learning or read about it or already develop it yourself, right? So you can get, obviously, it's not super new topic right now. So you should know some, at least I'm pretty sure that a couple of people here should know like what can go wrong here with machine learning, why it produces on physical. So anyone wants to, again, unmute themselves or like chat here?
Yeah, I believe something is wrong with the repulsive part of the potential, no?
Yeah, obviously, right? So it's super, super wrong, right? But that is the biggest problem that many potentials still have, unfortunately. But there are ways to fix it. People just kind of ignore it for now, more or less. But there are some correct ways to fix it. In any way, so that's totally correct answer. So if you look at the dissociation curve of H2 with ANI1CCX, so it looks like that. So I didn't plot, unfortunately, here. I might redo it at some point. But it's actually have very, very small, like going up like here. So it doesn't have much of the repulsion, right? So what happens, of course, if you start your dynamics from some point here, it rolls up down there, then it just rolls over to the second, like to another side, right? Potential, which is totally
exactly.
It's totally unphysical, but machine learning can do this. And so, like, there is this simple way to check is this behavior. You can just do this scan, and then you see whether it works. And so if you look at like full CI, obviously doesn't have this, right? So it's has repulsion. So unfortunately, again, I didn't plot it, but it's of course going very, very high. And then MP2 would have correctly. So this is another approach I will talk a bit later about. So they all have like physical models. They all have correct repulsion, and dissociation depends, but like at least to some extent is correct. Right? But machine learning potentials can give you anything. Like even it has like second minimum, so you can try to optimize. You will find within this potential. Second minimum, you can try to do dynamics here. So if you what saves machine learning potentials people and us like would work on them a lot is that usually your data contains this like a bit of repulsion region, right? And that's why it kind of implicitly learns, and then when you run MD, you don't see these things often, but sometimes you do. And that's why when you run like normal simulations, it's usually like it has more reasonable shapes than for H2. So that is a particular problem for H2. But if you use this ANI1CCX for some other molecules, like water molecule, for example, you will not see such a behavior anymore. It doesn't mean it's also good for water molecule, like at dissociation limit, so it will be also like this. But at least like when you run molecular dynamics at room temperature, it will be reasonable, right? So, but here particularly, it really hiccups very badly. And again, it's not because it cannot do it, it's just because developers are busy making these models generalizable to different organic molecules and other molecules. And somehow H2 is not interesting enough to play with, but actually it's a fundamental problem. So, and you can incorporate this physical information into model too. So that's some people try to do. So you need to be aware of these disadvantages, of course. And of course, if you train yourself machine learning model, particularly for H2, it's super easy to generate data, right? It's just like one-dimensional problem. So you just do a scan. So calculate many energies for different like interatomic distances with your favorite level. And then you can train machine learning model, and we have like instructions in the course how to do that on this, like even full CI data, because H2 is very small. You can generate yourself full CI data. It's not a problem. And then you can do dynamics, and then it will be correct. So that's what my students do usually. So they play with it, and then they can make it correct. And here is like just a script giving you a taste how it usually looks like. So you get some data, and then you get some energy data set. You can label yourself. So Melaton can label with DFT or full CI. You can try to do that. And then here you say, okay, train it with some ANI models. There are many other models. And then save in some model file, because you want to reuse it later, right? So you save your model somewhere in the file. And then you can use it so you train it on this molecular database, and then you get some model which you can use later for dynamics. So that's pretty straightforward, but there are many models, and that will be a bit of one of the topics of my lecture. So far, is it like, do you have some questions or like any comments, like topics you want me to cover? So it's a good time to steer my talk in some direction. So if not, I can continue. So this okay, you used ANI model, I used ANI, but Cracker usually I give a lecture, so but ignore this, so I didn't update this slide. What is usually called machine learning interatomic potentials I already introduced. Here's a bit more formal introduction, is that it is a simple function which produces energy based on your nuclear coordinates, plus, of course, very often like what kind of nuclei species you have, what chemical elements you have. So the power of machine learning is exactly that it has this ability to predict you almost any property you want, given enough data. And if you have a good like neural network, that can be done. Now, the problem is that there are many machine learning.
Good slide.
Yes.
Good slide. Good picture.
Yeah, so that's by my graduate student who already graduated for Chunga. So I really like it. So that was his idea, and I put it now in many talks. So he worked on this implementation of different machine learning potentials in our MLAtom software, so that you don't need to play with all this different software, because it's actually a big mess. So like every software, every package has their like conventions you have to learn. So we try to produce, like you saw in PutFast, right? You just put the name of the potential, and then it works for the same way, more or less, on your data set as any other potential, and then you can play with it. So that's why he spent lots of time interfacing all of this, and at some point he came out with this like very beautiful stuff.
Yeah. Pavlo, let me use this slide to do a question. Yeah. One question I have is, what do you think about the way to produce a machine learning potential in terms of the future? Because recently I could see some groups and guys exactly they are debating in literature to build a kind of universal, okay, machine learning potential where we can apply it for many different systems instead of, for example, to build a kind of a specific machine learning potential for a system. So basically, we have two ways to work with that: build a kind of a specific machine learning potentials, or try to develop kind of a universal machine learning potential. I'd like to have a comment from you, and also if you believe that's possible, for example, to develop kind of a universal machine learning potential.
Yeah, so I have a section on that later on in this lecture, because that's one of our main research topics also in the group, to develop universal potentials. And that's exactly like, but
Good.
because you asked, so maybe we are not even going to talk much about like all of these intricacies of machine learning potentials, but jump into this state of the art. And I don't think it is even a question of whether we need like specific or universal. I think we need both as usual, and it depends what you want to do. And also many universal potentials have a very good feature, which I will also show later, is that you can fine-tune them, so you can use them in some ways to get faster to the resulting final potential on your data. In a way, so you can have your specific potential, but you reuse weights from the universal potential, right? To some extent. So you
Yeah,
can benefit a lot from that. So
I
that's
got it.
why I don't think it's like a big problem in terms of debating which way is correct. It's like we need both. So like architectures, we need new architectures, we need new solutions, because there is always something to improve. None of the potential is perfect. And also there is for observable futures, there is a need to tune them to some specific problems, because we apply them. So we develop potentials, but I also now shifting more and more to applications. And then I see very often, okay, we have this new problem, and then somehow our universal potential doesn't work for it, so we need to do something about that. And of course, when we generate more data, we can update our universal potential and so on, but very often we kind of roll back to like fine-tuning them on some specific system. So right now it's still kind of a bit, I would not say that there is single universal potential that replaces DFT right now, but people go into this direction, some serious companies like Meta. So our solution is also combine, like usually we combine some empirical methods with machine learning potentials. I will show that later. And then that's already something that you can use already pretty robustly for many applications. So that already works quite good.
Good.
So I will thank you for the questions. That's why I can more or less skip many of the things, but I will briefly show like what we attempted to do back then, 2021, and now many things changed after this. So we tried to answer first like which potentials to choose. It's still a question, by the way. So it's still a question, but we benchmarked many different types of potentials, and I'm not going to go into technical details much about them. So our own potentials were like from the crack family, Cambridge regression, and so on. Nowadays, almost no one uses them for like routine research. So even in our group, we develop this and we don't use them, right? We switched to neural network potentials. So we develop now based also neural network potentials for many reasons, but probably the main reason is because, as it often happens, some things are just much more popular, and there is more effort into that and more libraries, right? For example, like Python. There are probably better solutions than Python, like Julia language. But because of all these libraries, people stick to Python, because once you want to move away from Python, you end up going back to it because there is some library which you want to use, right? It's kind of, although like Python itself, like really pretty bad for scientific purposes, because it's not back compatible and all these environments drive people crazy. But anyway, so like we also use Python. So our Meraton package is Python, because no better practical solution. And that's why now we use neural network, because again, no better practical solution. And honestly, it's very flexible. solution right now, and with all these GPUs accelerations, it's really saves us lots of time. It's also quite beautiful in terms of flexibility. So you can combine many things inside and then play with losses. So it's now our main tool. So we almost forgot about so this paper that we published with Mario recently that you mentioned at the beginning, we still used kernel methods there, kind of for legacy reasons, because we got very good results. And it was so one thing about kernel method, it is very fast and good for small data sets, and then for tests, it's perfect, right? So to develop some procedure, to understand how to do something, it's perfect. But then when you want to scale up, move to big data and so on, big systems, then it's a problem, and that's why we try to use neural networks. Okay, so we try to answer this question now. It's kind of clear that neural networks win, and equivariant neural networks are now kind of considered state of the art, and they have very big advantages in terms of accuracy, but big disadvantage, they are super slow. People try to accelerate them with some success. So things might happen and change, but right now, if you have lots of resources, it's the way to go. So if you can parallelize your training on hundreds of GPU cards, surely is the way to go. So you should do it. But if you don't have much resources, then it's a limitation. So that's why you might fall back to some of these AMI networks, which we love to use because of our hardware issues. Right? So again, we have many of these implementations of these different potentials. So you can change method based on simple input and then use it. For example, geometry optimization. So that's very simple. So I will not go into to describe any more theory about kernel-rich regression, but neural networks have this nice feature that you have this fixed number of parameters and then you just optimize them. Although it also kind of now depends because there are some message passing things which update many things on the fly, but that's a different story. Okay, so one big thing about neural networks is that they use this gradient descent and learning rate. And very important thing to mention is that neural networks always give you different results fitted on the same data. Right? So if you're looking for reproducibility, you have a bit of a hard time. You can make it produce the same result with some tweaking, but nobody does it. It's too much hassle, and then at the end, it just not going to simplify enough. Right? So you just have, so most of people just accept that neural networks give you different results and make use of that. And you can make use of that by taking multiple, so average of multiple neural network predictions, and then you get more accurate prediction, more stable prediction. And another very nice feature about that is that if you take deviation between neural network predictions, you can kind of estimate prediction uncertainty. That is one of the standard techniques which is done for active learning, for example. I will talk a bit about that later. So that's why I stopped here a bit and mentioned this because it's kind of important to understand that if you train your neural network and your classmate trains another neural network, and then you get different results, don't be surprised. So it's normal. But you can average, so you can combine your neural networks and average them and get uncertainty. So it's not bad thing. Now, another important thing about neural network potentials right now is that most of them use this locality approximation. So what does it do? Instead of predicting total energy directly, you learn this total energy as a sum of atomic contributions from every atom in your molecule. And then you usually can predict this atomic energy by taking into consideration neighbor atoms within some cutoffs. So there are some message passing schemes trying to get messages from other atoms, like more distant atoms, and do it during learning so that you know how far you have to go in terms of your environment to get reasonable result automatically during training. But still, it is a limitation. right? Because whatever you play with it, or whatever you play with it, you will end up using this approximation. So sometimes it just doesn't work. Right? So you can imagine some cases, you can think about them when it will not work, but the typical cases are like very conjugated system and other things. So sometimes it will not work, but for many practical purposes, luckily for us, it does work. That's why it's so popular. And again, like there are some theories.
Pavlo. Using again this slide, okay, and this explanation, and having, for example, exactly your recent paper published about the quantum descriptor and the importance of the quantum descriptors for the machine learning potential. So, can you comment about the importance of carrying the descriptors that you want to use in your training and models?
I think it's super important, although underappreciated, yes. But it's also about simplicity sometimes, right? Because if you want to develop potential which depends on some property, quantum mechanical property, so potential should be usually differentiable because you want to predict forces. And then it's sometimes a problem in terms of implementation because, for example, you want to take partial atomic charges, right? As your from quantum mechanical simulation as your descriptor. It might improve results, and I think some people try to do that. But then, if you want to do molecular dynamics, it means you will have to, first of all, you will have to do these quantum chemical simulations. So it's cost, but also you have to take derivative of your charges. Right. So that's why it's like it depends. If you just so what happened in our paper, so first of all, we don't predict it with quantum mechanics anymore, but we can predict quantum mechanical property with another machine learning model, right? So that's why you sometimes, so that's another trick. So you can first solve a problem of descriptor, choose the appropriate quantum chemical descriptor, then train machine learning model on that, another one, and then integrate it in one workflow so that you use one machine learning model predicting descriptor, and then the second machine learning model using this descriptor to do final prediction of your target property like energy molecules, right? So that's a good question because I think there is still lots of things we can do to improve simulations based on descriptors. So that's for sure.
Yeah, thank you.
Yeah, and okay, so that I was just talking about. So I will not talk much, but cutoffs, right? So you always cut something off, and then you have to take care of your what happens later. Right? So that's why these popular potentials, they all had some kind of cutoff. So message passing is another thing that I mentioned, but basically you kind of have your own descriptors because it tries to get more. So I need a better slide for this, but basically you get messages from other atoms farther and farther away, and then until you are happy to predict your property. So equivariance seems another important dimension here that again talking about descriptors because that's kind of inspired also in a way by quantum chemistry because they use this the same like for basis sets basically functions which take into account that if you rotate a molecule, right? So that's the same problem in quantum chemistry. So if you rotate a molecule, so your like dipole moments rotate, your like orbitals rotate, everything rotates. Right? So that's why you want actually equivariance of, so that if you rotate your descriptors and also you rotate your property which you predict. So that's why it's what these equivariant networks in a simplified way are doing, and that's why they actually were shown pretty impressively that they deliver very, very accurate results. Because so that's turns out to be important property and important descriptors to use. So for equivariance. All right, so that's something I was talking about, and then so like you need to, once you train, you have some errors. But before I talk about other topics, so one thing that you should keep in mind is that quality of simulation is not equal to the quality of fit. So even if you set aside some test set, which is standard practice in machine learning, you still might have very bad performance in simulation. And that's an unfortunate fact, but that happens a lot. And that's why you should be very aware that until your model works very good in simulation, you cannot claim that it's a good model. So there is no shortcuts here. So you need to test it in the application you want to use it. So if it's molecular dynamics, run dynamics and see whether your molecule collapses. And molecule can collapse in many different ways. I will show you later, but also you see before, like for H2, right? So that's what can happen. So that's not good. And yeah, so that's why. Another thing which is, I don't know how much time I want to talk about that, but because many people have physics background here, and it's a bit provocative slide because with machine learning models, it's also related to something I want to talk later. So with machine learning, we have a bit of a problem with this concept of total energy conservation. And not a problem in a way that we cannot get energy conservation, but we have the opposite problem, so that we get these flat lines of total energy, right? So which is perfect. That's what exactly you want to see when you run any molecular dynamic simulations in this NV ensemble, right? So you want to see flat lines in terms of total energy. You want total energy conservation. That's something we learn always in physics. And that's why when people see these plots, they're very happy to see them. But we have a problem here because that's people don't talk about that, because these lines don't tell you whether the model performed well in this simulation. So you will get this flat line also for this H2 example I showed you. But that's totally unphysical trajectory. So you cannot get two nuclei colliding through each other and going through each other, right? But then you will have total energy conserved. So we have a problem here, right? And I think it's underappreciated, but basically what my claim is here, and my solution is that we should go away from this, right? Because as long as the force is negative derivative of potential, energy, it will be energy conserving for small time step by construction. And machine learning potentials, they're very good at this. So they're very smooth functions. So they have these auto derivatives. So you will not see any bumps here unless you use very big time step, right? But as long as you use small time step, you will not see any deviation from from this energy conservation. So it does not mean it's good. And then you will see all of this. I like to show this, like anyone CCX, so for H2. Exactly, so that's exactly what I was telling. So for H2, it is flat line. But for anyone CCX, you see like sometimes, so like you saw this colliding, but if you push it from the other side, it can also dissociate H2, which is also in physics, right? And so it depends how you do your dynamics. So you will see that it's wrong, but you have flat line in total energy. And some potentials here I show, like also MP2, if you take very big time steps, so you will see discontinuities in total energy. So you will say, oh, it's terrible dynamics. But when you look at the actual evolution of H2 bond lengths this time, it's reasonable dynamics. It's not that bad. So these total energy bumps, and this is like looking very scary, right? Total energy is not conserving, at least. But it actually is the best compared to full CI. So we have a problem here, right? So it means that we cannot judge by this definition of total energy when we talk about simulation accuracy. What we have to do is we should really compare to the conservation to the exact total energy, because energy conservation law in physics, it doesn't tell you that it should be conserving for your potential, for your machine learning potential, or for your DFT. What it tells you is that the system should conserve exact total energy, like in our case in classical molecular dynamics, in vacuum, right? So if it doesn't interact with any other particles. So it just should be flat for exact total energy. And the problem is we, of course, don't have exact total energy, but we can do like we can calculate potential energy at some couple cluster or some good level which you trust. And once you do this, so you will get this kind of curve. So you don't have flat lines anymore, but then these non-flat lines will reflect the quality of your dynamics. So it's a bit like theory, and probably I should not go too deep into that, but that's something to maybe inspire some of the young minds to like think about it differently. So like when you talk about total energy, you should think about which total energy. So it's not machine learning energy, that's for sure. And if you have full CI, perfect. If you don't have full CI, like right couple cluster, even some at least as good DFT as you can get to. So then when you add it to kinetic energy, then you can calculate potential energy plus kinetic energy, you can get total energy. Okay, so that was a bit like probably a bit off topic, but I wanted to emphasize that you should be careful with evaluating. So general guidelines for evaluating quality of dynamics don't work in machine learning. You can have terrible dynamics, but very good total energy. All right, so I will skip most of that because it's a bit of theory, how you evaluate potentials and so on. And we had a good time talking about other things, so I will move more to universal potentials, which you mentioned. And if you have questions about theory, I can talk about that. So like before that, one way I should mention is it's not enough to have potential, right? You need data to train it. And that's what you previously had to do with active learning, and still you might have to do. So that's when you do molecular dynamics, you sample points from there, you calculate quantum chemical data for it, like energies, DFT energies and forces, and then you train your machine learning potentials, you run again dynamics with it, you check uncertainty with your deviation of neural networks, for example, and then you repeat this until you sample enough. So I will not go again much about that, but that's still quite important topic. So this also has lots of theory. What I will talk about is that actually we now move into the field of universal potentials where we don't want to generate ourselves data. And again, like I was already kind of spoiling a bit because Luciano asked me, but you still might need to end up doing this, but in a different context of fine-tuning. So in any case, our goal is to use machine learning potentials in the same way as you would use semi-empirical or DFT approach, or any other quantum mechanical approach, or your molecular force field, right? So you don't want to, for every system, find new parameters for it. I mean, in force field community, I know people still fine-tune and change the force field parameters for their systems. But in principle, you really would like not to do that, right? You would like to take machine learning model and just use it, like just to get your answer and get your dynamics. And that is exactly what this universal potentials all research is about. You try to make them work for different molecules without training them specifically for this molecule. But there is huge progress there. Although, again, it's not perfect. There are still hiccups and problems and so on. But the progress in like recent years is really impressive. So like this UMA potential is like trained on over 100 million molecules data set and so on. So these potentials are really amazing. We have our own potentials too. So now we also combine a lot, so that I will talk about it later. But if we talk about machine learning potential specifically, progress there is enormous. And even if you complain right now about some problems, they're getting solved pretty fast. Okay, so that's why, what are universal potentials, by the way? So that's a big question too. So there is no universally accepted definition of universal potentials. Some people say it should cover the full periodic table. If it doesn't work for all elements in chemical, like all chemical elements, if it doesn't work for all full periodic tables, then it's not universal. I disagree with it because in my ANI1CCX, for example, one of the first potentials, it is universal model because it does work for many molecules, right? Okay, it doesn't cover the full periodic table, but it describes pretty well organic molecules out of the box. And let's be honest, like even semi-empirical methods, many of them don't work for all elements, or don't work equally good for all elements, right? So what's the problem? Even quantum chemistry is not universal then, but obviously it's generalizable. So that's why I would call them universal too. And it depends how, so my definition is basically if it works reasonably well for reasonably large chemical compound space, it's fine. It can be universal. Depends what is reasonably well and how large is your space. That's all very arbitrary and all very subjective, but you should be aware that there is no accepted standard definition. So just you will see in literature many different discussions about that. It doesn't matter right now for practical purposes. Just if it works for you, why not? So it's universal. All common feature of these potentials, they were trained on loss of data. And ANI data sets used for ANI1CCX data, so they were trained on 4.6 million geometries, DFT geometries, and later fine-tuned with transfer learning to ANI1CCX a couple class quality. And so that works too. So do you have any questions at the moment, and what topics we can steal? Still have many topics to cover, but I can skip a few.
Professor, I have a question. This delta ML has to do with the active learning procedure inside this part, or it's another stuff?
Okay, so delta learning is a bit here jumping ahead. So that's my specialty. So that was my one of my first contributions to the community is delta learning. So okay, I think I need to have some slides. I found it. So delta learning is actually a very, very cool concept because it's very simple too. So instead of learning your full CI energy, couple cost energy, whatever energy you want to learn directly, what about correcting some faster method like Hartree fork or semi-empirical method? Or if you work with molecular mechanics force fields, why not correct molecular mechanics force field with machine learning to get ab initio quality, right? So think about you have some bad method and some good method. And good method is expensive, but bad method is cheap. The problem with bad method, it is not very accurate, but at the same time, it is good enough in terms of physical properties. So it has, for example, for H2, again, I like this example H2 because it's simple to understand. You see there is a minimum here. So it will not dissociate molecule, it will not have this improper paneling of these two hydrogen implied. So it is correct. But when you look at the errors to more accurate, it is pretty bad. But machine learning can correct it to the good level, and then you don't have this dissociation. So it is more robust, and it's also more accurate than if you try to learn directly on machine on the target level of theory like TFT. So does it explain it or?
Yeah, I think I understood. So you can mix actually a bad machine learning model, or not bad, but
yeah, kind of
not so good machine learning model with and try to extract the best of them to come up with something.
So it is kind of very interesting because you mix up two bad things. You mix up bad semi-empirical method, right? And then you mix up bad machine learning model. And then you end up with something which just works better than both of them. So it's kind of like this synergetic effect where one enhances another, right? So it's very beautiful, and
Yes,
it works
yes.
very nice. So that's exactly what we've done in the kind of data learning approach. So this ANI model, which I showed you before, it is pure machine learning model, right? So it is pure machine learning model. It is has no of these like we call it baseline, like semi-empirical method or something. And it can have these very bad problems like H2. But once you combine like semi-empirical methods with this correction, neural network correction, which is also a funny type, by the way, right? So we use the same bad kind of model, and we use the same data set even to train it, right? So we use the same data set. But once we combine it with semi-empirical method, it starts to work much, much more robust way. The price you pay is lower, but it's still fast enough because we use semi-empirical method on many things. So it will not give you this dissociation of H2 anymore. So that's the good news, right? So I was showing you. So that's what this delta learning is doing. So thank you for the question, because you know I
Okay,
explained it.
thanks. Thank you very much.
Yeah. Okay, good. So okay, now like we were jumping a bit about ahead with this data learning things, but in principle you have this situation very often. So you have lots of data in which you can generate at some low level like DFT. And I'm talking here, DFT is already expensive, right? But still, there are even more expensive methods like couple cluster. And, and then at couple cluster, you have very, very few data points. And then you have a problem. So of course, you can use data learning as I showed you before, but then you will have to do it with DFT speed, which is slow. But another thing is to consider. So let's think about it, take a step back, and what can we do with these data sets? First one, we can train separate model on DFT data, then we get pretty good precision, right? So, but accuracy will be off because DFT might be not very good. On the other hand, if you train on couple cluster data directly, well, you will get you will get closer to your accuracy, but the precision is so bad that it's also not very, like at the end, not very accurate. So you can still have quite big error. So that's a problem. So on the one hand, you have small data, which is more accurate, but you cannot get from small data like good enough model with small error. On the other hand, you have like lots of data at some crappy level, and then it's not very useful for your application. So what to do? So one typical solution in the literature, except for data learning, right? But, one way which people do is transfer learning. So you already have your model pre-trained on DFT data. So you keep it. But then you let it know that there is this better data set and only slightly changes parameters. And when you slightly change its parameters, you will end up now with high accuracy and high precision. So that's why it's a very nice approach. And then if you ask me what is better, data learning or transfer learning, my answer is, well, look at this slide. So actually we combine here data learning and transfer learning. It's not about better, you can combine them, right? You can correct with machine learning model, and then you can fine tune this correction on like higher quality corrections. So
That's yeah, Pavlo. Yeah, that's an interesting idea. I have a question about that.
yeah.
Yeah, how about the state of art of doing this in practical way? How many how many you know uh, how deep should be your transfer learning model,
Hmm.
or how many labels you need to have the layers to get a very good accuracy and precision. This can maybe vary about the data you have as an input file, depending on the system, or
Yes.
you can have a kind of a standard, okay, layers to get a very good results using the transfer learning model.
Yeah. So that's a very good question because we investigated it quite a lot, but we cannot give you like 100% universal answer, unfortunately, because it does depend a lot on the data sets and many scenes property you want to do. So one thing is that we, for example, for the Sunny networks, we have some standard layers to freeze, which works kind of okay for most of the cases, and then they defaults, and then you can use them, and then you will be on the safe side. But if you have enough like patience, resources, and so on, then it is always recommended to play yourself to find the better settings. So that's why, unfortunately, there is no like perfect solution to that. Also, people try to play a bit more, so you can even like do transfer learning not just by freezing some layers, fine tuning, but you can actually add more, like add some heads of the, so they call usually multi-head, or like add some additional heads of neural networks. So basically some additional neurons to your network, and then train them, which will be much faster. And then you don't even touch most of the or any of the parameters of the previous like model, right? And then you just train the small addition to the neural network. Which
is it possible, Pavlo? Is it possible to automate the process of optimizing the number of layers in your model? Yeah, is it possible to automate this process?
Because basically considered like hyperparameters are many packages to do this hyperparameter optimization. That's super expensive stuff, because even training is expensive with neural networks. Right? That's why I was talking. It depends on your neural network, on sources, on your data. So if it's affordable for you, yeah, you can do that. But usually people still like end up doing it semi-manually or manually, because it's so expensive that you can only run a couple of experiments, and then you just do it by hand, right? Because you can vary very few scenes by hand, and then if it's expensive, you will see better what's going on. That's why, unfortunately, no. But again, software getting better, and then all these fine-tuning scenes, universal potentials, more experience people get. So we have our own implementation of this fine-tuning on your data, so you can try it. So kind of, again, if you use defaults, you'll be on the safe side, but it will. So you just need to know it will not be optimal solution for your problem, because none of these scenes are usually optimal for your problem. Neural networks have too many parameters and too many layers for your problems anyway, and then so you don't know nobody knows what the optimal solution of neural networks, unless it's a very small system and very, very small like toy problem. All right, so that's why lots of neural network stuff is, and machine learning research is really kind of art and lots of trial and error. It's not like, even in quantum chemistry, there is lots of trial and error, but there at least you have some theory which can guide you. I was implementing myself quantum chemistry since. So you still have something which, like, if you do it properly, it might look properly, right, at the end. But here it's like you try to do everything properly, and then you can get worse results. So it's lots of trial and error until you get more better feedback. Okay. So one thing that we kind of recently introduced, and that our favorite toy right now, in terms of how we do this training, is not do this transfer learning at all, but we still kind of end up. So again, nothing of this is exclusive. So you can combine this. So we combine transfer learning with this approach to just giving you some spoilers. But in principle, like another approach which we introduced, which is in principle, again, fundamentally a bit better than transfer learning, is this all-in-one training, because actually you can train on both levels at the same time, and then your neural network will learn from both of the levels, and then it can make predictions at any of these levels which you train on. So you just basically provide us a new label for labeling your method, or even experiment if you have experiment. And once you do this, so for example, you say to neural network, okay, now I want to make predictions at couple cluster level. And then you just, okay, it will predict you at couple cluster level energy. And then you say, okay, I want prediction in DFT, and then it will predict the DFT. So and then you can combine it, making some delta scenes, and then combine with delta learning. Right? So it is none of this is exclusive. There are like so many options right now, right? It's getting a bit hard to follow, but this is our current recommendation if you want to play with different data sets, because we get usually better accuracies in doing this transfer learning other things. You have less decisions to make, because here you don't even need to know what you need to freeze, what kind of like you were asking how to do this transfer learning properly, which right here you don't need to think much. You just put this together and then you just train it. Fine, it's done. So fewer decisions to make, better results at the end, and then you can use this in many different situations. So that's why it's now actually it was, so I didn't update it, but it's got published in JCTC recently. Okay, good. So, and accuracy is pretty decent compared even to equivariant neural networks like Mesov published in JAX, very popular network, but our results are even better. Okay. And we used any network which is simpler, but modified it with this all-in-one. All right, so now, so I was talking about this, so I was kind of looking at it back. So how to fix this? Again, I said delta learning is a way to fix it if you want to get more robust quantum chemical simulations. So we already discussed that. I just show you that for delta learning, you have this AKM1, so which is really has proper. So it's still not perfect. It's going a bit weird here, but at least it will not give you dissociation, and then it will not. It still helps correct retention. So that's why it's a better approach. All right. So we have some other things which might be interesting for you. I don't know how much, but that's more about chemistry. So you can use it to run. That's another AKM2 level to do this downhill dynamics, to get lots of trajectories very fast. And actually now the quality of these delta learning potentials, universal ones, we cannot even call them potentials, kind of, because they have some empirical methods. Yeah. But people call them potentials, so I don't fight with that. I also use potentials for convenience. But the quality of them is really getting very good right now, because we can get to couple cluster accuracy for many applications, and compared to DFT, it's very often much better than DFT. And then you get error bars. And remember I was mentioning about these like uncertainties. If you have different neural networks, then you combine them, you average predictions, but you get error bar as standard deviation between them. So that's why it is fast, accurate, and trustworthy, and it's really now like can be used out of the box for many. All right, so I think like I have many topics to cover, but like before that, like for example, I have adiabatic dynamics and so on. So I don't know how many people interested in this other topic. So that's why let me ask you like first, whether you have questions about previous ones, any other questions, and like what topics you're interested to discuss. Yeah, anyone?
Yeah, if you want to, if you have time and if you want to go ahead, you can. Here with us we have students, that are working with DFT as well, and also MD simulations, and also some empirical quantum methods.
Good. And like for adiabatic dynamics, I don't know how many people interested in this topic, because I know like there is a very vibrant community who are interested, but like is this audience like I don't know what percentage of people would be interested in that. So like anyone wants me to go ahead, I actually don't see the chat. So if you chat, maybe it's better if you unmute yourself. Or okay, so I don't see any new chats. But anyone is interested in anxiety state, then I can talk about that. And I have one final topic which I would like to wrap up it, which is kind of a very interesting one. So, but before that final topic, I can also briefly probably go about anxiety states, because that's we worked with Mario a long time on that. So it's I have many things to talk about that, but I will not. So I don't want to take too much time. something which would be too boring for most people. Okay, so I don't see many people interested in that, so that's why I can safely skip, I guess, most of it. I will just say that it's super much harder thing to do. That's why we spend so much time on that. So I can go back to these things if again anyone is interested. What I will just mention is that even active learning looks much more difficult if you compare to previously. So, all right, and if you talk about universal potentials here, then there was no universal excited state potential until this year. So we were the first to manage to get one. So that tells you how difficult this thing is. It's like super difficult topic to do, but now we kind of finally managed to get some excited state potentials which are approximating TD-DFT, which is not a bad thing. So they're better than some empirical methods for UV spectrum, which is quite an achievement. I'm not saying they're perfect because, again, they're machine learning potentials. I already talked to you about problems for ground state. Here you can imagine there are even more problems, but they're decent, and they are the first to do this. So that's why something to celebrate. But there is still lots of work to do. For example, if you run dynamics, you might get something weird like that. But one potential thing which you can do with them, which we use now like all the time, is to again do transfer learning. So if you do transfer learning on them, then with transfer learning you will get much more stable molecular dynamics faster. And I'm talking about excited state dynamics, which is even a bigger problem. And then if you do this transfer learning, then you get with much fewer training points stable dynamics. And that's, again, regardless of whether it's excited state or ground state, you usually get much faster to your target goal when you do transfer learning or like fine-tuning of your universal potentials than you do it from scratch. Right? So that's why we kind of, and again, here we used actually all-in-one approach with transfer learning, so it's a bit complicated. We have some scripts to do that automatically. All right, so like I want to really finish it with the most interesting topic in terms of concepts for molecular dynamics. And so I asked you like how we can accelerate molecular dynamics with machine learning. I got many answers. So I give the last chance to everyone, and probably people are tired, but if you got any other ideas how you can accelerate molecular dynamics with machine learning after everything I was talking about. So any ideas? One last chance.
Hey guys, please
Yeah.
feel free to share the message, okay, in the chat if you
Right.
don't want to talk. If you want if you have some questions, please do like Alexandre did. Put your question or your answer for these questions in the chat, okay? Please, Marcelo.
Professor, I think can you explain what do you mean by accelerate molecular dynamics? Because I'm trying to come
Make
up
it
with
faster.
huh?
Make
Sorry,
it faster.
make it faster in what terms? In the simulation itself, or in producing the potential, so to say?
It produces a trajectory, right?
Okay, yeah. Okay.
That's simple. Right.
Mm-hmm.
So you already like see many like solutions. People said like, okay, you can predict directly a result of simulation. Just fine, you can do it.
Because I'm using right now um, deep neural network to train a potential, but I noticed that depending on the number of layers or the number of nodes, the training takes really long time. Also, the simulation also resulted from the training potential also takes ages to finish. And yeah, I don't know if this is a problem with the configuration sampling or if this is a problem with the architecture. I believe the architecture influences, but I believe that decreasing the or lowering the architecture model, but increasing the configuration um, would would enhance the potential model, I believe.
Yeah, we can discuss it later because it seems to be already like specific research problem, right? But generally, it of course very much depends on the architecture and other things. Like if you take simple architecture, like we usually do, you can fall back to the simple architectures, and then if you do this fine tuning and other things of universal models, it will be much faster. Like this fine tuning usually takes much faster time than doing it from scratch, and also like people start to think and develop this kind of uh, stepwise approach that you have bigger model and then you try to train smaller models based on some in some way learning from this bigger model, right? And then you use this smaller model to do simulations faster. So that's one way to do it, and that's why we most of the time do fall back to smaller models because, like probably we have limited hardware resources as an academic group, so we don't have hundreds of GPUs, and then we have to deal with this hardware like speed issues. So we don't have much choice, but use this combination of these smaller models, fine tuning, delta learning, and many of these tricks to make it work. So there is no universal, unfortunate answer, but we have similar problems and some solutions. Okay. Anyone else? Questions? Or like again, answers to this question.
Yeah, so now answering this question, I believe that depending on the problem you want to investigate, I think there is no rule of thumb to accelerate MD with ML. I believe. Okay. I don't know if, but
I mean, there is no universal one, that's for sure. But anyone has some suggestions, like concepts, ideas?
Yeah, Pavlo, thinking about that, I believe in great part of the code of MD simulations, 30-40% of the time consuming is to calculate the forces. So the forces is the problem, okay? To have a very good algorithm to run fast MD. Yeah. And then machine learning, I think it could be work on it maybe.
Okay, so but that's again, we can predict forces directly. We can predict it as derivative of energy, which will fall back to machine learning interatomic potential. Right? All right, so I will not take much time. So let's go to the answer. But see, so I was like, and before I go to the answer, just keep in mind that because the answer will be very, very simple, and then keep in mind that will be like that in this next couple of minutes that once you see simple solutions, they seem trivial, but actually coming up with them is a trick which is very hard in science. So, but you might find simple solution for simple like for complex questions, like complex problem, if you ask simple question and find simple solutions. So in your research. Okay, so let's go to the answer. First of all, once we do it with machine learning, like potentials, then we do this MD. What we usually do is like this, right? So we do prediction of the next geometry, and then we calculate forces. We predict forces for this, so we predict another position, nuclear positions. Then we calculate again forces for it, add it to the trajectory, right? So predict another one. And then why I'm showing this? Because it's trivial, right? I'm showing it because it's painful. That's what our computers do, but that's painful, right? Now, we actually don't need to do this, and we don't want to do that. Because think about it, like I was asking you before, right? So like I was telling you before that you can think about machine learning, what we want to have as input and output. And if you think about molecular dynamics, actually you don't want forces as output. You don't want energies as output. What do you want as output? You want nuclear positions as a function of time. So you want as input time and as output nuclear positions, right? So why not do that? Because neural networks are capable of doing this. And that is pretty, like, if you do it in time steps, like you can increase time steps, and people try to do it now with machine learning too, but you will end up with also different solutions. And that is also not very nice because you don't get smooth function. And to predict this point, you cannot do it unless you predict the previous point. So it's very badly parallelized and so on. So if you think in hindsight, doing dynamics in stepwise way is actually a very terrible idea, right? Because we don't want to do that at all. We just have to do it because, and had to do it previously because we didn't have any other choice to do. So we had to do this because simply we didn't have a better solution. But now with machine learning, we do have a better solution. We can predict nuclear position as a function of time. And okay, so the answer now seems very simple, I guess, right? Because it's obvious. It just seems so simple, but also like raising the question, is it even doable? Because that looks very ambitious. And that's, again, that's why research comes into, so that's not trivial at all. So the idea is simple, solution, and is kind of possible, but it's not trivial. So we first started actually not even with molecular dynamics, but with quantum dynamics. So we showed it is possible to learn like population as a function of time. So that was brilliant. But it took us much longer to get something with molecular dynamics because it's actually a much more complicated problem. You have multi-dimensional system, so you have so many atoms and like so many degrees of freedom, and now you have to learn all of this in this four-dimensional space-time. So you're not just learning it in XYZ coordinates, but also as a function of time. So your like data you need to learn is huge. But it doesn't mean it's impossible, right? So that's why we've done that. So I like to call them 4D space-time because they're actually a bit more than molecular dynamics acceleration. If you want to discuss, I can talk a bit later. It's very important for chemists, by the way. Maybe not so much for physicists. Because it contains in neural network all information. So what is chemical reaction? Chemical reaction is actually the same molecule which transition in time to another molecule, right? Or like molecules, whatever. So, but it's actually still the same object, which the only difference is just time. So these neural networks, they learn even chemical reactions as a function of time. So they condense 4D like space-time into one neural network object for molecules, which is super beautiful. And then it has some applications for reactions, which I actually have some slide about it. But so it is much more universal than machine learning potentials too, because if you take derivative of positions as a function of time, you get velocities. And if you take the second derivative, you get acceleration, and then you can get forces, and then you can kind of integrate, get potential. Right? So, and that's all as a function of time. So that is much more, it's even generalization of machine learning potentials in a way. So it's much more beautiful, and it is doable. Much more complex than machine learning potentials. That's why it takes so long time for the community to adopt, for us to develop, and it takes time, but it is doable. And we showed first for simple molecules, like so that was by the way just one molecule here, but we did it for 10 other molecules, and for reaction like azobenzene dehydrogenation. So it is stable. It is like you can predict like 1 nanosecond, no problem. Very fast. So like 1 picosecond trajectory with 0.05 femtosecond is you can get in 1 minute. That's just super fast. It is much faster than machine learning potentials because you don't need to do the step-by-step integrations. So okay, that's a bit like neural network simplified way, but here is a time with different machine learning potentials like MolMod-CS, which you're already familiar with. I showed it a lot. And this 4D space-time model, which predicts nuclear coordinates directly, is 100 times faster than even MolMod-CS, which is already very fast. And we did it for 10 other molecules, so it's robust. And I was mentioning about chemical reactions, so you can analyze what is important chemical reaction, which is kind of important for chemists. So now we managed to put this preprint that generalizes it to different molecules and also periodic boundary conditions and so on. So it is 100 times faster than machine learning interatomic potentials. It works for different molecules. The question is like how good and so on. So it's still under investigations, but at least we were the first to come up with this model. So unfortunately, again, we don't get much attention from the community. That's why we don't get even much feedback from this. And the things we can test is limited ourselves. But it exists, so you can download it. So again, it's an MLAtom, so you can try it yourself and see how it works, and then complain to us. We'll be happy to give any feedback. Because that's the future. That's how you want to do machine learning, like accelerated molecular dynamics. Anyway, you don't want to do it step by step. That's
Pavlo. Is that stable on time?
Yeah, so you can do it like 1 nanosecond, no problem.
Yeah.
But again, so there are some problems because we cannot predict what will happen in 1 nanosecond time. It's still too far away behind the horizon, right? So what we can predict within first 10, maybe 20, maybe 50 even femtoseconds, right? So we can predict these within these time segments, and then we kind of have to stitch them together, right? So it's at the end it becomes similar to EMD in a way that you do need to take stitch it together, right? So but it's not really time steps because you don't need to propagate at every 0.5 femtosecond to get robust MD. You can make predictions at 10 or 20 femtoseconds, which is basically impossible with current MD integrators and so on, propagators. So that's why it is, and again, fundamentally it's different approach. So, but dynamics itself is quite stable, even 1 nanoseconds for many things, not for probably you'll find some molecules it will not work. And we only generated data for relatively small molecules and trained on relatively small molecules. So when you want to predict more complex molecules, okay, so here's just some small molecules power spectrum, so it does work. But if you want to predict even bigger, dipeptide, it's already quite problematic, so we had to fine tune it. But again, see fine tuning. So we have universal model. We can fine tune. So it is definitely not going to work for something like super complex system with, I don't know, hundreds or thousands of atoms until you fine tune it. But it will work after you fine tune. So that's the good news. And here it was just showing you. So if you want to predict with any potential with 4 femtosecond time step, like with ANI1X or with DFT, it will start dissociated molecule because it's 4 femtosecond time step for any MD. It just will make so much trouble for you on dynamics. It will be unstable numerically, right? It will start dissociated things. But if you predict dynamics with 4 femtoseconds kind of steps, then it will be very stable with our approach. Because again, it can predict pretty far in the future, but not too far. So that's a limitation. Okay, so any questions about this? That's kind of different topic.
Yeah, pretty good idea. Quite interesting.
Yeah, it is, but again, not enough attention from community, so potential is underexplored in this approach. We had very big struggle to publish the first paper. We now have trouble publishing the second paper. And both of these things were highly non-trivial. It took my best, or one of the best students, his whole PhD to do these 2 papers, kind of. Okay, he published many other machine learning potential papers, but for example, I was highlighting his slide with this zoo of potentials, right? So he did many papers, but for this topic, he only did 2 papers because it's super hard to do. And also because we didn't get enough attention from the community, so you need to get grants, you need to get papers for students, so we couldn't put too much effort into But potentials are enormous. So if people start doing this and investigating this and using it, you can accelerate so many scenes. Like you will save so much time in dynamics, and you will get so many new insights which you couldn't get previously from any MTV approach. But again, so like if you get inspired, anyone in the audience, I would be very happy, because I'm always talking about this and somehow it's still not picking up. So, I always say like, okay, in 5 years it will explode, because I see already now many preprints attempting to do seamlessly. People start to pick up, but it's so slow. Like if you had a bit of time in terms of ideas, then you'll have a really hard time to convince people to do that. And once it's exploded, then everyone will say, oh, why we didn't do it before? So I will believe it will become hot topic. So you might be very early if you start doing it yourself right now. And then, or if you use our models and start improving them, I'm happy to collaborations, because again, this student graduated, and because it's not taking too much attention from community, and cannot afford putting too many people working on that. So I will be happy for any collaborations to put our effort together so that we can move this needle, like convince the community that it's a useful approach. People will realize it, but it will take some time. For example, data learning model was and paper had also lots of trouble to get published, but now it's like cited thousands of times and used in many approaches. So just take time for these things to pick up. All right, so it's a bit of like my scientific curiosity, and it was my favorite project for a very long time. So I can talk forever about it, so I will not talk much about it. So like we also can predict something to food for thought. You can predict dynamics directly as a without even as a function of time, but just directly the whole trajectory. So that's another interesting approach. So we did it for quantum dynamics, but for molecular dynamics, I don't see like much interest in that, but possible. Okay, so like maybe like I was saying, it's the last topic, but that's basically when the movie finishes, you have some other scenes like rolling on the screen in the cinema. So that's why it's like where we all going in the future with AI. I believe it's like agentic AI, so we'll really have autonomous AI scientists. And then if you want to, right now, like if you do computational chemistry and you want to say to agents, okay, simulate the infrared spectrum of a molecule, that's already not any more science fiction, so it can actually do that. So I will show here a video. So like first you can ask to generate some geometry, then it will generate geometry. You can view it online. So that's, you can register that for free. You can play with it. And just a bit heads up, we are now trying to deploy newer version. So maybe in a week, it should be even much more better than the current one. So if you have problems with this one, the next version will be much more robust. And then, so here you just basically asked to calculate infrared spectrum by a chat, and then it produces infrared spectrum with our AI models, which produce accurate results within minutes. So all of this, basically 2 minutes of chatting, and then you get a result which is comparable to experiment for this infrared spectrum of this molecule. So that's already not any more science fiction. We're already in this agentic AI, which I didn't have time to talk, and then it's not the topic of the lecture, but we're also working on having molecular dynamics done this way. So you chat and say, okay, run molecular dynamics is my potential, or like is this for this space model, get trajectory, analyze it, whatever, right? So we're working on that too. You will see it in the future. Like if you subscribe to my channels, then you will see it there, like Facebook, YouTube. You will also see it on Slack, so I post there. And before that, I will show it again, but before I finish, I would like to thank all my group, because I really done all of this work which I showed. So now you can talk about it, but they were doing all this. So a very great team. So thank you very much for your attention, and now if you have further questions and so on, I'm happy to answer.